His area of specialization includes partial differential equation, computational, fluid dynamics, mathematical modeling. He served as the principal and director in charge of MBA program at Oxford College, Karnataka in the year 2007 to 8. And he was the founder and chairperson of Hubli Education Trust at Karnataka in India in the year 2008 to 11. He has more than 38 years of experience in teaching and has published many papers in national and international journals. He has also served as a reviewer for the international journal Atmospheric Environment. He has presented many papers in conference and delivered lectures in computational fluid dynamics and mathematical modeling. Once again, I welcome you, sir. Participants are kindly note this. Any questions kindly type in the chat box, which will be addressed in question and answer session. And also mute your video. Sir, now the session over to you, sir.
Thank you. Thank you, one and all. Good morning to all the participants, remote participant, but reaching all over the world. I welcome you all. And let me begin my lecture. That is, the title is Urban Air Quality Assessment using a Mathematical Model. This particular title is this lecture is in this particular lecture, going to study the detailed study of urban air quality assessment using a model. This mathematical model, what is the purpose of developing a mathematical model? The purpose of this mathematical model helps to understand the mechanism of transport of atmospheric pollutant in the urban area, how they behave, how they travel after they emit due to the traffic flow in the urban area, how they travel in the wind direction, in the vertical direction. So that mechanism we will be understanding by this mathematical model. And using this mathematical model, that is getting the solution out of it, we will be able to know the pollutant distribution quickly and cheaply than monitoring network. As you know that in the monitoring network or monitoring stations of air pollutants study, that a lot of expenditure is required, is involved, and it is a very long process. But sitting in the what you call classroom or in your office, we can do the mathematical modeling of air pollution problems. And this is the main purpose of developing the mathematical model to study air quality assessment. Let's go quickly to two important aspects here. One is, what is mathematical model here? So what is mathematical model? In fact, if you look at this, can you remove this top, this thing? Hello? Yeah. So mathematical model is a simplified description of physical reality expressed in mathematical term. In a very simple way, it is defined here. What is mathematical model? So we have a physical reality, physical what we call phenomena. That's a three-dimensional thing. That we are replacing it by mathematical terms, and that's the mathematical model. And here, the process of developing a mathematical model is called the mathematical modeling. So here, we are going to look into what we call the mathematical modeling process in three parts. We have a real world problem. Then we convert it into mathematical thing, that is a mathematical model, the second part of it. This mathematical model, we solve it and we derive the results. That we do the prediction, and this prediction will be compared with the real world problem, and then we interpret the result. So this is a cycle here, and this whole thing, that is converting the real world problem to mathematical model and deriving the results and then comparing with the real world problem. So this is what the whole process is called, mathematical modeling process. Let's begin with model development. So that's what we call it, atmospheric diffusion equation. And here there are two approaches to study, to develop any equation. One is the Lagrangian and another is the Eulerian approach. And here we are considering the Eulerian approach. So the concentration of pollutant, that is CI, that is there are n pollutant species, they must satisfy the continuous equation, that is a equation of mass. So that is time, then you have advection and then diffusion. And then we have here the CI is the what we call pollutants, UJ is the velocity, and I is the rate of generation, that is by the chemical reaction, and this is the addition, that is the source. And this is what the basic atmospheric diffusion equation. And using this is our base for developing a what we call mathematical modeling of air pollution problem. So let's start with what we call derivation of the basic equation to study the air pollution problems. We know that whenever we have a conservation of mass and that is equation, then we have a fluid velocity uj and the temperature T. They must satisfy the momentum equation, that is the Navier-Stokes and the energy equations respectively. So we have three coupled equations to solve. One is equation of mass, momentum, and energy equation. But the pollutant occur at parts per million in concentration in the atmosphere. So therefore, the pollutant will not affect the meteorology. Meteorology means it is the study of air in study of air near the ground. That's the meteorology. So therefore, the equation of continuity can be solved independently without coupling with the Navier-Stokes equation or energy equation. So therefore, if I want to know the complete description of the pollutant behavior, it rests with the solution of only the equation of continuity, what we discussed earlier. But the things are not so what we call rosy here. The thing is that the flow of interest is turbulent. That is, our atmosphere is turbulent, not laminar. Turbulent in a simple words, it is irregular and random. So therefore, we apply the stochastic analysis, and we divide, we decompose the fluid velocity into two parts. One is the mean part, that is deterministic, and another is perturbation part, which is stochastic. Now we substitute uj, this two component we substitute in the equation here. This equation we substitute, and we get the equation of continuity becomes this. Next, now look at it carefully. Once we substitute uj as these two components, deterministic and stochastic, and look at it, this ci is what we call linear with this, and because of this, ci also becomes turbulent. In the sense, uj is random. Therefore, the solution of equation of continuity is also random here. So what we will do here is, again, CI is now split into two parts. Here, this is called the ensemble average, and another is the stochastic. So ensemble and the deterministic earlier is that in the deterministic, that is UJ, where we what you call divided into components, that is average over a time, and this is average at a time particularly. And substituting these two in the again in the equation of continuity, we have this, the equation reduces to this. But we have another big problem. Look at this equation very carefully. Here, the number of dependent variable is more than the equation. And this is what? The term. And this term, so this term, if I want to replace again, I mean, if I want to do just to make it again, then again we have a more number of dependent variable. So this is, in the turbulent theory, this is called closure problem. So where we have a more dependent variable than the equation, and that is the closure problem of turbulence. This is all happens because of the turbulence here. So what we need here is that we need to close this. That is, we have to make the number of dependent variable equal to the equations. So what we do, we require additional equation, which gives rise to new dependent variable and so on. If I add another additional equation, that's so therefore we have to close this so that the number of dependent variable and the equation becomes equal. So what we do here is that to close this, we give rise to new dependent variable. So therefore, we assume that turbulent is a eddies of, what we do here is that turbulent fluid we consider as a eddies of fluid. What we do here is that the turbulent flux here, we compare this and to this by mixing this, that is called theory. And what we are going to do here is that this particular term is now replaced by the fixed law, that is where the diffusion is taking place in the direction here. So therefore, this term is now replaced by this, where JK is 1, 2, 3, 1, 2, 3 here. And when you look into this tensor here, and here all the non-diagonal elements are 0, and we have only diagonal element. So therefore, I can replace JK by JJ here. So therefore, I will put this in the equation there. When I put this equation, and this, what we are going to do, that this term is now replaced by first order. That's why it is called the first order closure, or you can say K theory, or we can say big single length, what we call theory here. Further, we have some more what we call assumptions here. One is the molecular diffusion is negligible, and this term is negligible compared to the turbulent diffusion here. So therefore, we neglect this. Then we assume the atmosphere is incompressible, obviously. So therefore, this term becomes 0. And we consider the pollutant is chemical inert. That means it is not reactive. So therefore, we take Ri is equal to 0. So therefore, substituting this and then neglecting this, making this 0 and Ri 0, we have this equation. So can you please remove the top one? So here we have this equation here. The equation reduces to, I will expand this, then the equation in terms of x, y, and z is this. Now this is basically, now it is the atmospheric diffusion equation which predicts the spatial and the time concentration of the C with the proper initial and boundary condition. But this is the basic atmospheric diffusion equation. Now I will apply this basic differential equation to the urban problem, area. For that, I will go for some assumptions. Here, the first one is the x-axis is aligned in the actual wind direction, that is east. The y-axis is aligned in the crosswind direction, that is the north-south, and the z-axis is vertically upward. So this is how we align our x, y, and z-axis. And the pollutant concentration does not vary in the crosswind because the pollutant is carried by the wind in the x direction, because we are aligning our x-axis in the wind direction, that is in the east. So therefore, I can consider this crosswind diffusion and crosswind advection and the diffusion 0. Therefore, our call three-dimensional becomes dimensional. Next, horizontal advection is greater than the horizontal diffusion. So this is much more than this. So therefore, we can neglect this and then we retain this. Now, vertical diffusion is greater than the vertical advection. So that is gone. And then we are going to consider the short-term air quality, that is hourly, diurnal, that means daily. So therefore, we retain the time dependency. So look at this with the earlier assumptions, these and these all assumptions, we are now arriving at the mathematical model which predicts the air pollution in the urban area, and that is this one. So this is the time, then we have a wind speed in the x direction, and then kz is the vertical diffusion, and this is what the simplest mathematical model. And here, to look at this, here we have to just define the domain now. So we calculate the concentration in two different what you call layers. One is called planetary boundary layer, which is from 1 to 1.5 kilometer from the ground, and another is within the planetary boundary layer. We have a surface layer which just 50 to 100 meter, where we all live and where we all breathe air pollution. So this is a very important layer. So we need to calculate the concentration of pollutant in the surface layer, that is a 50 to 100 meter, and it will go in the vertical direction up to 1 to 1.5 kilometer, which I will explain to you why I put this 1 to 1.5 kilometer, why it is varying, why it is not fixed. So that we will discuss in the later stage. Now we assign the boundary conditions. So since it is a time dependent, so we have an initial condition here. So when t is 0, and this L is the what you call the length of the urban area, and this is the height of the what you call urban area, and V0, I say C is 0, that means no pollutant when T is 0. So the moment T greater than 0, we have a pollutant which is coming from the left side, that is a background concentration of pollutant. So we cannot just say that there are no pollutant at all. The pollutant will be always there. So we consider that on the left hand side, when x is equal to 0, that is from 0 to h height, and t greater than 0, there will be some pollutant in the urban area. Now, for the boundary condition, it is more than enough because we have a first order. So we have a what we call one boundary condition here. Since in the z direction, it is the second order, so we need two boundary conditions. So that's the consistency of a partial differential equation. So this Q is the emission rate, and this is because of the traffic flow in the urban area. So the emission is Q when z equal to 0 from 0 to L. This is the length of the what you call urban area X is going on there. And beyond L, that is beyond this small L, then there is no emission, that is 0. And that is from L to capital L. So this capital L is the desired distance, whatever we want to calculate the concentration. So in my what you call model, I've taken this small L as 6 kilometer and the capital L as another 6 kilometer. That means totally 12 kilometer. I have calculated the concentration in the wind direction. And upper boundary condition, that is at Z is equal to H for all T, there will be no pollution will be escaping here. So let's see that how I maybe have this particular condition, and for that we need to go into the some what they call metrology, some of the basic metrology thing to understand here. So that's and this is very important. All the mathematicians should not forget that whenever you develop any model, I mean uh, having a partial differential equation, you need to check the well-posedness of that particular partial differential equation. That is, the solution must exist, the solution should be unique, and the solution depends upon initial and the boundary conditions here. So you need to be very analyze this before start solving any problem, and this is being taken care, and these all have been in the error analysis. I have already worked on that. Then we have to look into ill conditional problems, and where small change that happens in the data leads to the large error in the solution. And what happens is that we are replacing the partial differential equation by algebraic equation. And because of this, we have errors, what we call propagate. And that is also we have taken care in the computational fluid dynamics in the numerical analysis. So let's come to little what we call meteorology aspect. That is how our atmosphere is there, how the pollutant which are released into atmosphere, how they behave. So this is a simple what you call. Let me give you first of all, what do you mean by exactly the air pollution? Normally, a city is what we call ventilated, and it is having two mechanism, major mechanism. One is horizontal wind flow to move the pollutant out of the community, that is laterally as well as horizontally. And there is a vertical diffusion always take place. Look at it, this vertical diffusion takes place because the sun, what we call, heats the earth becomes hot, and with that the layer above the earth becomes turbulent, and then the vertical diffusion takes place, and this vertical diffusion move the pollutant from near the ground surface to the upper level of the atmosphere. And what these two things very important that here, that wind flow moves the pollutant out of the community, the horizontal and the vertical direction, lateral direction. The diffusion moves pollutant from the ground to the upper level of the atmosphere, that is beyond of the surface layer. So these two are very favorable for what you call not having a air pollution, but it doesn't happen. So what happens that either there will be no wind flow or there will be no vertical diffusion happens, especially after the sunset and before the sunrise. And these are the condition, as you know, that wind is always changing. So what happens is that in a city, these two mechanisms, as long as they happen, I mean, they go, continues, there will be no absolutely air pollution. But unfortunately, both things doesn't happen. So one of these stops. When that stops, then the air pollution occurs. So that is what the main, what we call meteorology of this particular urban areas. If you look at the model, this is what the urban area, and I have considered from zero, that is from this point. Actually, and then this is this point, that is a 6 kilometer I have taken the urban area, and 6 kilometer further I have calculated here. And this is the wind direction where I have aligned. And now because of this wind, the pollutant are what we call advected here, and because of the what we call diffusion, the pollutant are emitted. The pollutant are emitted as well as what we call diffused in the atmosphere. And this is what the height, that is the mixing height I say. I will just explain to you in the later stage. If I plot the concentration of pollutant versus the distance, that is a downwind distance, then the concentration will be in this particular aspect. It will be like this, that you see that the pollutant gradually increases till L, because we have pollutants from 0 to L, that is the pollutant are mainly emitted in the urban area. So therefore gradually they increases, and beyond L, the pollutant, there will be no what you call emission here, so they gradually decreases. And this direction, that is to the rural areas, etc. So in other words, it is just like this. We have a rural boundary layer here, that is on the left side, and we have a rural, and that's what the background of pollution come. And this is what our urban area, and the pollutant are carried by the wind. And look at it. This is you have more pollutants here, and then the pollutants are carried in this direction, and these pollutants are carried to the next rural area, and that is what the it is urban area. Urban air pollution is not a local phenomena, so it is a global phenomena. Look at this now. This is a very important. I told you that how that we are going to set our upper boundary conditions here. Usually, if I look at the temperature profile of what you call atmosphere, the temperature is versus the height, it is always decreases. And then after that, suddenly it increases here. And this is called the inversion. And this inversion, where there is a decrease and suddenly increases, this is called what we call inversion layer. And when the pollutant are released in the what we call in the urban area, where they are released, and remember they are trapped in this. And this height is 1 to 1.5 kilometer maximum in what you call in urban area. So I will explain to you in the later stage how to, I mean, we are going to fix it here at in this case here. So this is what the generalized mathematical model, physical layout of the model which I have developed. And here we have a X, and this is the emission from 0 to L, and then we have a crosswind, and then we have a background pollution, and these are the boundary condition I mentioned here. And in the model what we are discussing today, there are no chemical reaction, and there are no washout phenomena. Chemical reaction means what you call, if I am considering the chemical reaction, then I will have to have two partial differential equation coupled, because the primary pollutant is converted into secondary, and therefore I have to solve two coupled partial differential equation. And there is another phenomena called washout. Because of the rain, the pollutant are deposited on the ground. So this is also considered either in the boundary condition or in the governing equation. And there are some pollutant are escape, that is what we call leakage velocity, we call it. And there are some pollutant which are, because of the weight, they deposit on the ground, that is called dry deposition. So these are all what you call the removal mechanism or the chemical reaction that take place. And in my thesis, I have considered all this, but for today's discussion, I'm considering without all these removal mechanism, or only I'm considering the time dependency, advection, and that's all. So now the comes is the stability condition. It's a very, very important that how the pollutants are affected by the atmosphere. The question is here is the our pollutants which are released in the urban area are governed by stability condition. So what is this atmospheric stability condition, which is the main what you call thing, which what you call causes the air pollution? But here I've just given you some what you call here in our mathematical model. What we have discussed, there are two basic what you call meteorological parameter. One is the wind speed, that is the mean wind speed, and another is the turbulent diffusion. So interestingly, the atmospheric stability is characterized by the length by this equation, and for neutral condition and stable condition, the profile for turbulence is given like given by this. And these two what you call profiles, which has been experimental, not analytical. These are all experimentally tested, and it is being used in the literature of in all the air pollution study. And these are the two profiles which I'm using here. And here I have mentioned the condition. Number one is the neutral condition, and another is the stable condition. So what is this actually these two conditions? These two conditions are atmospheric conditions, characteristic of the atmosphere. Let us understand this by a simple diagram here. Look at it. This is a very interesting, what we call diagram, but it gives you the complete idea that how the pollutants are affected by atmospheric stability. The atmospheric near ground, if you look at it, the wind speed at the midnight till the sunrise, it is almost laminar. It becomes turbulent, and it reaches the maximum turbulence at the noon time, and again it decreases, and after the sunset it becomes a laminar again. So what basically happens in a day, that is daily, is that before the sunrise and after the sunset, the wind speed is laminar. And after sunrise and sunset, with the noon maximum, it becomes turbulent. So look at this. This wind speed causes the, this is happening because of sunlight, that is the light, what you call heat received by the sun from the to the earth. So our turbulent diffusion is all depends upon the wind speed and the sunlight, that is heat. So if you look at the what you call atmospheric point of view, from midnight to sunrise, this is what not a good thing for the pollutants. From sunset to midnight, happens here is that at this period, that is midnight to sunrise and then sunset to midnight, these two conditions are called stable conditions. And this where the what you call the maximum what you call turbulent happens, or the maximum speed happens here because of in the noon, this is called unstable condition. And what is neutral condition? The neutral condition is just before sunrise and after sunrise. It is a very, very short time. And after sunset, before sunset. So such is a very, very short time. Neutral conditions happens here. But most of the time, the stable condition happens. That's why you see the maximum pollutants after sunset. You see the fog in the big cities, as you see in Delhi or any big cities. So what happens here is that we have a what we call stable conditions here, we have a neutral here, and we have a neutral here, and then again we have a stable condition, and this is what the unstable condition. So what this stable, unstable, and neutral condition does? So the stable condition, they suppress the mixing of the pollutant with the atmosphere. The unstable condition enhances the mixing of the pollutant with the atmosphere. So this is a good thing that on the point of view of the air pollution, therefore we are not considering this part of it. So therefore we are considering only the stable condition here, and will a small what you call neutral condition. To understand this again, let me give you an example here. If I look at the stable air, how it flows, if we have a ground level this, and when the air flows, and look at it, the air flows because of the pushes and the rising air, and look at it, it again comes down. And this is bad for what you call air pollution, because whatever the pollutant are emitted in from the ground, so they are not raising up, I mean they are not mixing with the atmosphere, so they are again what you call making it what you call a kind of inversion here. Whereas in the unstable case, the pollutants are which is emitted at the ground, and our what you call the stable unstable condition mixes goes up, rises up, and this is rises down. So therefore the pollutants are carried in the high in the atmosphere. And to understand this very in the simple diagrammatically, this is red one is the pollutant, and this blue what you call profile is the stable condition. What happening is that the pollutant are retained here, and if the same thing in the unstable condition is that the profile is opposite and the pollutant are escaping high on the in the atmosphere. And in the neutral, what happens is that neither it is what you call increasing or what you call decreasing. So therefore, this condition and this condition are not good for the air pollution, but this is not at all here, need not worry here. So therefore, in my, in most of the urban pollution models, we consider only two stability condition. One is the stable condition and another is the neutral condition. I hope I could make you understand clearly about this very what you call important phenomena in what you call distribution of the pollutant because of the stability condition, that which is the property of atmosphere. So the eddy diffusivity, what I have shown you here, I mean this equation for neutral and for the stable condition. As I told you, this is all obtained experimentally and which we are using in this model. And if I put it in the profile of this, so the profile of that eddy diffusivity in the stable case will be like this. And for neutral case, it is like this. And wind profile, let's talk about the wind profile. So what happens in the wind profile here is that look at it in our model, there are two main parameters which act as an input parameter for the model. One is the eddy diffusivity, that is the turbulent diffusion, another is the wind speed. So in the surface layer, the wind velocity rises with altitude rapidly. So therefore we use the logarithm profile here. And after that, it rises very slowly. Therefore, we use the power law here. So with that, the profiles is looking like this. This is what for the stable case. And look at it here for surface layer, we have a what you call logarithm, and then you have a power law. And in the neutral case also, we have a logarithm and the power law. So that is how we decide. I mean, we take up the wind velocity profile. And now we come to the main, what you call next aspect, that is the solution. What happens here is that we have a mathematical model, and it is impossible to find the analytical solution of the model what we have developed. So because the wind and the eddy diffusivity are the what you call function of height. So therefore, we need to go for numerical solution. And what I have done here is that I have used the Crank-Nicholson finite difference scheme is used here. And of course, when we are discretizing the partial differential equation into algebraic equation, there are three methods: finite volume, that is also called control volume, finite element, and finite difference. But finite difference is a better one because it is a simple and a powerful whenever you have a regular geometry. As you have seen in the physical model of, my case, it is a regular geometry. Therefore, I have used the finite difference technique. And this is the implicit, what we call finite difference scheme I have used. And if you look at here, the main, what happens now, we are moving from one part to another. First we have to have a knowledge about the partial differential equation. Then we have to have a knowledge about the methodology, the second part. And the third and the very, very important is called computational fluid dynamics. So this is a very, what we call new field emerging in mathematics. And very, what you call it all, this CFD has started in fact by the advent of computers. And I cannot say that the CFD is a science, but it is more than a science. It is an art that whenever we are converting the partial differential equation to the system of algebraic equation, that is, we do the discretization. So there are so many methods we have. I mean, so many what you call methods of which method I have to use, which is a better one, which gives me consistency. All that is art. It is not a straightforward thing. So problem differs. I mean, the method differs with the different problem. So actually, the whole CFD is having a 4 cycles here. We have a governing partial differential equation, that is the mathematical model what we have. We discretize this. So this becomes a system of algebraic equation. And this, for this algebraic equation we solve, we get, remember here, we get approximate solution, not the exact solution. So please remember that governing partial differential equation convert to a system of algebraic equation, we get always approximate solution. That means they have what you call not to be trusted, in the sense they are not 100% correct. So there are errors in this. There are so many errors. If you name round off error, machine error, convergence error, time step error, so many errors are there. But interestingly, in CFD, we can do the error analysis. We can measure the magnitude of the error. We can control the error. So all that thing happens in the CFD. So that's why it is I consider CFD as an art of converting here and then doing the error analysis. So how do we know that this approximate solution is the correct one? So what we do that, we do the convergence study, that is as delta x, delta t tending to 0. In our case, delta z also tending to 0. This approximate solution must give rise to the exact solution. And then what we do here is look at it. We do the consistency study. We do the stability study. We do the convergence study. So this consistency, stability study, and convergence study is a part of CFD. And these three things, what we call gives the impetus, I mean, what we call the authenticity for the approximate solution. And although we do the three things, but don't forget that the numerical solution always has to be compared either with the actual values available in the, available, or we can solve this governing partial differential equation under certain, restriction can be, for this can be, analytical solution can be obtained, and then under what you call the same restriction, so these approximate solution and the exact solution should match. So with this whole process, we are controlling the error here completely. So what I have done in my case, we have three terms in the mathematical model. One is the time dependency. So for this, I have used the finite difference, and I have considered the second order, which is a better one. And for use, this advection term, I have used the upwind difference, and this allows the effect of advection in the flow direction, although this is in the unidirection in the downwind. So therefore, this is the best method for this. So there is no need to go for a second order, and the first order is accurate, and it is transportive, conservative, and also interestingly, this is stable also. So therefore, for time, forward difference, second order, for advection term, first order, upwind difference, and for diffusion, I have used the second order central difference. So this, I convert this into algebraic equation. And that algebraic equation can be easily solved. They are all tridiagonal matrix. And we have for Thomas algorithm, which is very efficient and which can be used to solve any tridiagonal matrix of any order, and using that Thomas algorithm, and it is very efficient used in the computer and has been found to be stable, and there will be round of error, finite difference, it is being controlled here. So that's the the advantage of having the tridiagonal matrix. And the computation cycle is repeated, and of course when you give all the values to the computer, so we have to command the computer to stop the computation. So for the computation cycle, so 10 raised to minus 5 is the ideal steady state is considered here, and the ambient air concentration were obtained for only 2 atmospheric stability condition, which I discussed in the earlier one. So verification of the code has been done, consistency analysis is done, and the convergence study has been done, and the residue fall is studied. And then very interestingly, this is the grid independent. That means we have considered different grids here. First 40 by 156 grid. This is the non-dimensional thing. I mean, exactly in the dimension way. So 40 to 156, second and third and the fourth. So this has been, for this, the contours has been plotted. And here I can show you, and this is the, residue fall. I mean, for different types have been taken for 30 seconds, 60, 90, 120, and plotted here. And what we see that for delta t 90 second and delta t 120 second, the concentration, the residue fall is almost same. So therefore, we have considered the time step as 120 seconds. And this is what here I mentioned, that is called the residue fall. That is a concentration residue obtained after a time step, number of time step, and the accuracy is guaranteed here. And the second accuracy is guaranteed here is to grid independence. Grid independence means the solutions are not changing with the change in the number of grids size. For example, look at this. Here we have 4 cases. This is for first 140, and this is for the second, and this is for the third, and this is for the fourth. When you see there is a much changes in these two, but there is no much change in these two. That is, I'm talking about this. That is, there is no much change in 160 by 624 and 240 by 1248. And there is no point in going for this because there is no drastic change from here to here. So therefore, I will consider this as grid independent solution. So that's what I show here. You see, for the first, second, there is some major changes, but from the third and fourth, there is no major change. So therefore, we consider this, and there is no need to go for the higher one. So these two analysis, that is the residue fall and the what we call a grid independent analysis ensures that your solution is what we call is accurate. And here the what we call the pollutants ground level concentration at 2-meter height, 3-meter height has been what we call plotted, and this is for the stable case. And you look at it, we have gradually this is what we call urban area is up to 6 kilometer, and therefore the pollutant is goes on increasing. Since it is the stable case, it reaches to 250 microgram, and beyond the urban area it decreases, and up to 12 kilometer, so the pollutant is still having a effect, and this will have a really problem for the rural area which are situated in the downwind direction. The same the ground level concentration has been plotted for the neutral case, and if you see that again it is goes on increasing but not reaching maximum. I mean, it's reaching only 70 because it's a neutral case, which I told you it happens only just before sunrise and after sunrise, and before sunset and after sunset for a very small time. So when beyond this, what we call 6 kilometer, the concentration is decreasing, and it is just a 10 microgram in this one. So that's not a issue here. And here the concentration is plotted for different what we call heights. That is for 9-meter, 6-meter, 3-meter, and this is what the profile of what we call pollutant. And of course, at 3-meter, the pollutant is that is the stable case, and as we go and higher, the pollutant are decreased here. So our focus is only in the surface layer, that is up to 10 meter. So that's really what we call issue here. This is for the neutral case, the same, the concentration at 3-meter, 6-meter, and 9. So look at it, as you go higher and higher, the concentration of the pollutant are decreased. And then we have a concentration at different heights, different what we call X value. So 3 kilometer for all height, 6 kilometer for all height, and 9 kilometer for all height. You see that for what you call, as you go into the downwind direction more, the concentration is reduced here. But whereas in the 3 kilometer, the concentration for the first case, it is increasing here. That is the concentration profile for the stable case. Similarly, we have this is the neutral case, and you see the same, the height versus the C. And then coming to, this is what we studied, the what you call concentration of pollutant at various height, various distances, and with this we get an idea that what would be the what you call the pollutant concentration, and is it the concentration of pollutant in an urban area or within the permitted limit prescribed by the what we call United Nations or the governing body of any particular day. So this will give you here, in this case, we are going to do, but the most important thing in this model is you should have a clearly the 2 input parameter. That is a very important, that you should know the wind speed at the various height and the vertical diffusion at the various height. So in this case, let me go to this what you call model is considered. This is the model what we are talking here. So this is a very model here. An input parameter, mean wind speed and Kz. And of course, there are many research going on, and better and better profiles for U and Kz for particular areas are being invented or experimented, and we can update this particular model with the different profiles of Kz. And of course, the methods, I mean, the finite difference method and what you call the removal mechanism, I said here, for example, this is the general one. If you look at this, we can, some of the pollutant are escape in the upper atmosphere. That is called removal mechanism. That means pollutant load will be decreased here. And the washout, and this is the again a removal mechanism, because this is the pollutant are deposited on the ground because of the rain. And rain out is also there, and washout is there, two different things. And dry deposition, but the chemical reaction is always happens in the sense the primary is converted to secondary, so that is also an issue here. So these all removal mechanism can also be incorporated in the governing equation. And I have considered all this, and I have even I have worked out for the primary and the secondary pollutant, where I have solved two coupled equation, one for the primary, and that solution is being fed into the second equation, and that is also being solved. So this is what gave you the idea here. That is what is this actually, how we assess the urban air quality by using a simple mathematical model. The question is here, the word I have used is simple, because if your what you call model is a complex one, then you will not be able to get the solution for that. So therefore, it's very, very important that your model has to be simple as possible. And we may not be predicting the pollutants exactly, but at least we will have an idea that what would be the pollutant load in a particular urban area. So if you sum up all in this, if I sum up all this, in conclusion, if I want to study the complete air pollution problem, it is a very, very vast subject, because when you consider the elements of the air pollution problem, it starts with emission. That is, what are the sources of air pollutants? What are the air pollutants? And for this, you need to know chemistry. Then the emission, they emit the pollutants. And these pollutants are in the atmosphere. Then when we are into the atmosphere, we need to study meteorology. That is the study of air near the ground. That is meteorology. Here we give more emphasis on atmospheric stability condition, which I discuss stable, unstable, and neutral. And then after emission, and then after meteorology, we need to model it. So for model, we need partial differential equation. And before that, we need to have some what you call the properties of fluid flow. That means we need fluid mechanics, especially the fluid dynamics. Then this partial differential equation, with the help of fluid dynamics, we have a mathematical model and we have to solve. Therefore, we need to understand computational fluid dynamics. Then last part of the element of the air pollution is the receptors. That is the pollutant which is emitted in the emission. It released into atmosphere and it is received by us, you, me, our what you call material, the animals, plant, they are all the receptors. So to study this, we need to understand physiology, medicine, and the plant pathology. So look at it, the complete study of air pollution problem involves so many things here, but you need not go into that. So being a mathematician, you have one thing is there, start with fluid dynamics, go for study partial differential equation, and then the CFD. And this is the part which I have taken, but in this case, metrology is there, as well as the chemistry, physiology, medicine, and plant pathology. So that is also, I mean, I have this, I mean, I went to it, I mean, I have studied it, but not into the detail. Being mathematician, this is my area of the research. And of course, it is a, what you call, in all my presentation, you have seen that whatever required knowledge for this mathematical modeling is more than enough. But I've just given you the conclusion that the complete air pollution problem is having so many of the mastery of all this one. So with this, I conclude my what we call presentation, and I thank you each and everyone, especially my sincere thanks to management of SKPD and charities, and Mr. G. Ramesh, correspondent, and Dr. Mohana Shri, principal, and Dr. Vanita, IQAC coordinator, and Dr. Rani, head Department of Mathematics, and all the members of the organizing committee, and all remote participants. And so I thank my college, dean, head, Dr. Rawat and Dr. Naktal, and all my faculties, I mean the colleagues. I thank you one and all. Over to you, Dr. Rani. And thank you, everyone. Any questions? You are.
Thank you, sir. Sudha ma'am. Hello.
Yes, ma'am. Rani ma'am.
Sudha, Selva ma'am. Hello.
Hello. Tell me, ma'am.
Selva ma'am.
Yes, ma'am.
Now you tell the questions to sir ma'am.
Yes, ma'am. Yes, ma'am. Sir. Sir.
Yes.
Sir, one of the participants raised a question. The difference between stable and neutral situation.
Sorry.
Difference between stable and neutral situation.
Just now I explained. Let me to that slide. See, it's a very simple way. I have taken example. This one.
Okay.
Stable. This is the stable condition. If I red one, if I consider that is a pollutant, and this is what the profile. What happens is that this is the what you call profile of the air near the ground, and which what you call doesn't mix with the what you call atmosphere. So that means pollutant remain near the ground. So this is stable condition. Means the pollutant are not dispersed vertically. So look at it. If you consider the volume of pollutant and the volume of atmosphere, volume of pollutant is nothing. If the pollutant are mixed in the atmosphere, then we have no issue at all. But stable is what happens is that it doesn't allow the pollutant to mix in the atmosphere. So that's the stable condition. Whereas in the unstable condition, the pollutant are being lifted. That is, it is being lifted. See that this is the profile of the wind, which goes up. So it rises, the air rises. With this, the pollutant which are emitted from the ground also rises. So when it rises, so look at it, our pollutant, we are very considered that we are considering two layers in the what you call urban area. One is the surface layer up to 10 meter. If you look at this here, this one, you see this is the air we have. So here, this is what the mixing depth, and in that we have a, what you call, if you look at this, you see, yes, we have 1 to 1.5 kilometer is the planetary boundary layer, and the surface layer is 50 to 100 meter. So these is dangerous to human being, or what you call, because this is where we live and this is where we breathe. And if the pollutant are not mixed with the atmosphere, then the pollutant will remain near the ground and we breathe it. So that is stability condition. That is a stable. Whereas in the unstable, it enhances the mixing. So in the stable condition, the pollutant or this red is the pollutant which is pushed in the vertical direction, and thereby there will be no effect in the ground level. But in the neutral, what happens? Either neither mixes nor increases the mixing nor dissolves. So this and these two are what we call the conditions, and that is the what the difference between. So that means stability condition doesn't allow the pollutant to mix in the atmosphere, so that pollutant affects the human being. Whereas the unstable condition allows the pollutant to mix in the atmosphere, and its effect will be nullified. I hope it is clear.
Okay, sir. So next doubt is,
Yeah.
is this model effective for indoor pollution?
Yes, it can be what you call, it can make it as a one-dimensional, because when we are talking about the indoor air pollution, we have no air there. I mean, whereby the pollutant are being transported. So yes, there is a lot of work is going on, and indoor pollution study is a very simple one, because there will be no what you call, the most important is turbulent diffusion there. There is no turbulent diffusion, because the turbulent diffusion is the main thing here, and there is no air. And yes, the most simple way we can study the indoor air pollution.
Okay, thank you, sir. And the next query is latitudinal parameter of the Earth included in your model?
Sorry?
Latitudinal parameter of the Earth included in your model?
Latitudinal in the sense, this two parameter what has been taken in the what you call the model, that is the wind speed and the eddy diffusivity, they are the function of height. So because of that only, we will not be able to what you call solve analytically. So that's why we solve it numerically. So this u is a function of z, and kz is also a function of z. And that's what the profiles I have shown you here. The profiles these are the profiles for diffusivity, and this is for the wind velocity, and which is the function of height. And because of that, there are no analytical solution. So therefore, we go for a numerical solution for these.
Okay. Okay, sir. Next doubt is, will this model work even in this lockdown situation?
Model, yes, there is nothing what you call. Now, one thing I can say, during this lockdown period, there is no emission here. I mean, emission has come down like anything all over the world. You see that ultimately, if you look at this, I mean, the pollutants here, you look at this, the pollutant is occurs in the urban area, this, and which is being transported because of the wind. So of course, there is no human activity. I mean, of course, there is absolutely nothing, not like that, but there is, but drastically the human activity has reduced, and therefore the pollutant emission is reduced. And of course, the air pollution is also reduced drastically. So one thing I can say very clearly, that if we cannot say, one cannot say that there is no air pollution at all. There is nothing like that. There is a air pollution, but the atmosphere, the nature takes care. And as I told you, unstable takes care of it. But the most important part is stable condition, that is after sunset and till the sunrise. So this is the period where the pollutants are not dispersed in the atmosphere, and that causes the air pollution. And it is not that only because of the traffic flow the pollutants are emitted. There are so many activities, and there are so many sources of air pollution. So as long as human activities are there, the pollution is there.
Okay, sir. So the next question is, what is the behavior condition for discrete random pollution?
Behavior in the sense, can we elaborate on that, please?
That is the question, sir. What is the behavior condition number for discrete random pollution?
No, I'm
They
not
want.
able to get a question.
Okay, shall I ask one more question, sir?
Yeah, yeah.
How much variation is observed from mathematical modeling values to practical values estimated for urban air quality measurement? What is efficiency?
So here, there will be no exactly same. One thing is that numerical solution cannot be exactly same as the analytical solution. But we see, as I had error, what you call accepted error. If you look at it here, I have considered 10 raised to minus 5. So that's the what you call maximum we have taken that. Here, I will just show you here in the numerical analysis part. See, here 10 raised to minus 5, the difference between that. So this is where I stop the computation, and that is acceptable. Now, I mean, it is mostly accepted in the research world that 10 raised to, and moreover, always the numerical solution are compared with the what you call analytical solution under what you call constant, that is U and K. We consider as a constant, and we obtain the analytical solution, and then we compare it. And of course, the difference between them is up to 10 raised to minus 5.
Okay, thank you, sir. Sir, one of the participants want you to suggest some reference book.
References, oh yes, I missed it, I believe. Here, the best, there are what you call here, as far as if you look at the what you call the elements here, if you, for partial differential equation, there's no issue at all. There are n number of books are available on partial differential equation. Fluid mechanics, there are many. And metrology, I can suggest, but right now I can write to you, and then you can forward to all the participants in the later stage. And for CFD and everything, very good books are there. For metrology and CFD, I can suggest, I'm really missed out the literature and the references, and I will what you call forward to the organizers, and they will forward to all the participants in the later stage.
Okay, thank you so much, sir.
Yeah.
Rani
Second,
ma'am?
sir. One second. Participants, anybody have questions? You have to directly speak to sir, means raise your hand. Sudha ma'am?
Yes, ma'am. Just a second, ma'am.
One by one, whoever raised the hands, ma'am, one by one, unmute it, ma'am.
Yes, ma'am.
One by one. Hello.
Dr. Sarojini?
Yes.
Sarojini, are you online? You can forward your question.
Hello. Hello. Sudha ma'am?
Yes, Dr. Sarojini?
Okay, ma'am.
They are
Leave her,
not
ma'am.
able to unmute the
Okay,
audio,
ma'am. Leave her, ma'am. Anybody is raise the hand, ma'am?
Yes, ma'am. Unable to unmute the audio. Rani ma'am. Rani ma'am.
Dear participants, you have any doubt, ask in chat box.
Dr. Sarojini, you have any queries? Please forward your doubts.
Give it, ma'am.
Okay, ma'am.
From hello,
Yes, ma'am. Rani ma'am.
Khaleel sir. Hello,
Yes, Rani ma'am.
hello.
Rani ma'am. Can you hear me, ma'am? Rani ma'am.
Needing, ma'am, sir.
Hello.
Hello, Sudha, ma'am.
Yes, ma'am.
Now you start, ma'am.
We go for the vote of thanks. I express my sincere thanks to our resource person, Dr. Khaleel Ahmed, on behalf of Sri Kanyaka Parameshwari College for having readily accepted our invitation and helping us to organize this webinar. I'm sure this thought-provoking lecture has inspired our participants to enhance their knowledge in mathematical modeling techniques and understand the mechanism of transport of atmospheric pollutants. Thank you, sir, for creating a platform for us to do research in different areas of fluid dynamics. I also thank all the participants for showing their keen interest. Yes, ma'am.
You continue, ma'am.
I also thank all the participants for showing their keen interest in participating in this international webinar and forwarding your queries and suggestions. I thank our management members, our correspondent sir, Sri Gugilam Ramesh, our principal, Dr. T. Bhuvaneshwari ma'am, our vice principals, and our colleagues for their constant support and motivation to organize this event. Thank you once again to all.
Hello, sir. Sir, we will end the meeting, sir. Okay, sir. Thank you, sir. Thank you. Thank you, all the participants.
Rani ma'am, sir wants to talk.
Yeah, sir. Sir, you are in mute, sir. 1 second, sir. Sir, you are in.
Yeah. Thank you so much. And thank you all the participants. And if you have any queries, please write to me. I will share my email ID as well as what you call the references thing. And you're always welcome. And all the best. Stay safe and take care. Thank you, one and all.
Thank you, sir. Thank you, sir. Thank you, all the participants.